As we start to get closer to sort of cracking what causes aging, there is research emerging that really suggests that the most root cause may be DNA methylation and epigenetic changes. And so all of these interventions, don't take them lightly. I mean, they're powerful and, potentially just life altering.
Welcome to Commune. We are on a mission to inspire, heal, and bring the world closer together.
So in 2020, you conducted a randomized clinical trial that demonstrated that by adopting certain behaviors, people could reduce their biological age. And the paper outlining the conclusions of this study, I believe, was first published in the publication Aging in 2021.
Yeah.
And eventually this work led to the groundbreaking new book that you recently released titled Younger You, in which you outline a protocol that helps people reduce bioage and by extension also increase health span. So first off, congratulations on the book. It's fantastic.
Thank you. Yeah.
So I think that we all have a vague sense for what might help us live longer. But the notion that you've actually been able to connect certain choices or protocols with specific mechanism, I think is really, really compelling for people and helps people then make those decisions and reify them in their own life. So I'm excited to dive into that. But since we're not all doctors, I'll raise my hand, and certainly plenty of the people listening are not doctors. I think at the outset, it would be helpful to scaffold our conversation in a little bit of definitional work.
Sure.
So first off, can you take a moment to explain the difference between biological age and chronological age?
Yeah. So chronological age is, the number of birthdays we've celebrated, the number of trips around the sun. We can't do anything about chronological age. We tend to associate chronological age with, health and lifespan and all, always and generally perceive the older somebody is, the more likely they are to get sick, et cetera. So we attach a lot to chronological age, but it's really just a number. In fact, I would argue that we want to let it go. By far, the more important number is our biological age. So this is how fast our body's actually aging. We have been trying to measure biological age probably since Ponce de Leon, like time immemorial. We've probably been doing that. But in fact, now that we're in what we call the omics era, where we can look at our genes, we can see how our genes are expressed. It's a whole new world into being able to really rather sensitively and extraordinarily measure how fast we're aging. And this is changing the face of science, Jeff. Like, I can't even underline how significant it is. Capital letters. How we think about and how we conduct science, given these new tools, will forever be different.
It is fascinating. And I want to get into some of the methods that you discuss in your book for actually measuring bioage. I know that there's a whole number of different clocks associated with that. But before that, I wanted to untangle a little bit more definitional work. So there's a tremendous amount of fuss made about life expectancy, which over the course of the 20th century grew significantly. I think in 1900 it was somewhere around 46, and by 2000 it was somewhere around 77, and that varies on gender. And I'm talking specifically about in the United States. It's also worth noting that the average life expectancy has actually gone down over the past couple of years, even before COVID. And maybe we can dissect some of the reasons why. But lifespan doesn't equate to health span. And you elucidate this beautifully in the book. So can you delineate a bit between lifespan and health span.
Yeah. So lifespan, I guess, is, we could measure by basically when we die. There's no association with health. So we have done a great job in this country extending lifespan. And probably initially, in the early turn of the century, of course, that was also extending health span. Like, we developed antibiotics, we were no longer dying of infections, and we were suffering much less. So there were extraordinary early, medical changes that allowed for a longer life. But today, lifespan may be living in a skilled nursing facility, propped up on pillows with dementia. So you're not present. You're alive technically, but your quality of life is just, remarkably compromised. We're seeing this in our country quite a bit. I mean, our healthcare spend, the amount of years that we spend with significant illness, thinking about, the drugs that we're taking, the kind of medical care and interventions that we require, is extraordinary. I mean, on average, the last 16 years of our lives, we're sick. Most of us with multiple significant illnesses. I mean, if that's not the biggest, deepest sort of call to action, I mean, isn't it? It's just unfathomable, right? To think about your final 16 years, being ill.
Yeah, you talk about that in the book of, like, we hit 63, I think was the age that you give. And then the next 16 years is riddled with neurodegenerative disease or diabetes or cardiovascular disease, kind of the big killers.
Cancer.
And sometimes, and sometimes multiple at the same time.
Correct.
I think you included one of my heroes, Atul Gawande. He had a graph from his book Being Mortal. Can you describe, I know this is an audio platform, but maybe you could describe kind of what those graphs tell us about modern lifespan?
Yeah. So back in the day, again, turn of the century, we lived largely a good life, but it was short, and then we died kind of, relatively quickly. What he describes is a descent into illness. So rather than sort of a straight line across, the line is dropping down, commensurate with ill health. And it withers eventually to death. So it's lifespan without health span. So early, you've got a short but solid health span, and then basically you die. And then in the modern world, we see a deterioration of our health over time, and a lot of suffering in those final years. And what he argues, and this comes from James Free's work out of Stanford in the 80s, is that we can live robustly till the end of our years here, whatever those are, and then die, peacefully and relatively quickly. And we should be able to do that with, straightforward lifestyle changes. So that would be a straight, strong, healthy line, and then, kind of a precipitous, but, hopefully painless and peaceful death.
Yeah, I think this slowly descending line, like you say, is concomitant with a tremendous amount of suffering.
Yes.
But it's
and
also...
not just... Yeah, go ahead.
Yeah, but it's also and expense.
Yes.
Right?
And it's not just suffering for the individual, of course, because the individual is probably relatively drugged at that point. It's suffering for the caregivers, who are largely going to be family. They may be, and the expense. So if your money is going to be going towards big pharma and big, and hospital and skilled nursing care, and, home care workers, et cetera, et cetera. Yeah, that's right.
Yeah. And I think, you do such a good job in your book underscoring this idea, because a lot of people associate this kind of longevity movement with kind of the Silicon Valley biohacker, for example, and that it's very geared towards the individual. But I think, you do a fantastic job outlining the social or the societal dimensions of actually living a healthier life or having a longer health span. Because I think at this point we spend somewhere in the neighborhood of $4 trillion on quote unquote sick care.
Yeah.
And I think, the work that you're up to is really trying to undo that.
Yes.
And not only have impacts that extend to the individual, but by extension, the individual's families, as you say, and then our whole kind of medical complex.
Yes.
that we have. So
yes.
Yeah, it's something that's fascinating. So maybe
can I just color a piece in for this? So
please.
So yeah. Biological age, not chronological age, but how fast our bodies are basically breaking down, is the biggest risk factor for the chronic diseases of aging. And so, again, diabetes, cardiovascular disease, cancer, dementia, Alzheimer's, etc. Biological aging is the biggest risk factor. So when we're aging faster, we're increasing our risk for these illnesses. And I just, a quote from Morgan Levine puts biological age or aging as a profoundly bigger risk factor for lung cancer than smoking. So just to put it into context of how potent biological aging is. If we can change the biological age trajectory, so going back to James Free's work, if we can improve health span, to your point, we will, by extension, reduce the risk of all of those illnesses and reduce the spend. So reduce this incredible amount of money that's going towards, these heroic, it's not healthcare, it's just lifespan extension. And I want to give you may be heading towards this already in your questions, but they've calculated, so David Sinclair out of Harvard and colleagues working with him, just crunched some numbers and put a year improvement at a $38 trillion savings. And maybe in an order of magnitude greater. So if we could improve biological age or lifespan by 10 years, that would be like 380 trillion. I mean, the savings of focusing on biological age is just astronomical, the potential.
Yeah, it's jaw-dropping. I mean, I think we're talking right now, the scale, it's like 120 million people in the United States are diabetic or pre-diabetic. So you just think of that, and that's just diabetes. Yeah. I mean, so it is, so the scale that we're talking about, and boy, could we redirect that into organic and regenerative agriculture to actually hit the hit the front side of the equation instead of the back side of the equation. Boy, that would address all sorts of issues.
I think a collective psychic shift in our country and it really in the world needs to happen where we realize that we're driving the car, that it's our genes are not our destiny, and that in fact our quality of life, our health span is in fact up to the choices that we make. We are not victims of the illnesses our parents or grandparents succumbed to, or conversely, if we people who have longevity in their family may think that they're impervious. The reality is the choices that we make day in and day out are influencing greater than any genetic hand-me-down how well we live. And so there just a sea change needs to happen where we light on that and it changes how we are.
Amen. So can you outline some of the methods that you leverage and other people leverage for actually measuring biological age?
Yeah. So we're talking about gene expression. We're not looking at the DNA directly. We're looking at biochemical marks on and around the DNA that allow genes to be turned on and genes to be turned off. Just a little bit of background, maybe some folks will be interested. We mapped the genome in early 2000s, and we really thought that it would answer our questions, that it would be the Rosetta Stone for diseases. This is why you have heart disease. This is why you have dementia. Obviously, you know where this is going. We realized, in fact, that's not the case at all. In fact, it doesn't. There is no one gene, one disease relationship, except for the rare exception. And that really focused attention on the field of epigenetics. So epi above, genetics, the gene, and that's all the intricate biochemical happenings that allow genes to be turned on and off. And one of the most studied, actually the most studied, and one of the most resilient is something called DNA methylation. DNA methylation is when a methyl group, so this is a carbon and 3 hydrogens, is placed on a promoter region of a gene. So that promoter region will allow it to be turned on or conversely turned off. When there are a lot of methyl groups on this promoter area, that gene will be inhibited. It just can't open up and be turned on. Conversely, when those methyl groups are not on a given promoter region, that gene can be turned on. Starting with Steve Horvath, and there's a few people who came a little bit before him, but really Steve Horvath out of UCLA created the first biological age clock looking at patterns of methylation happening on the DNA. And his first 2013 clock, it's called the pan tissue clock because you can use different specimen like blood and saliva, et cetera, et cetera. But he created that and released it in 2013, and he was able to reliably predict age from in utero, where it would actually be a negative number, up to centenarians. And it was correlative. You don't want it completely correlative to chronological age, because then it would be only useful to tell age, right? Chronological age.
Right. Yeah.
But it was correlative with chronological age to 0.96. So it was really rigorously associated with chronological age. And it turned out that this first clock, and there are subsequent generations of clocks, but this very first clock was more predictive of morbidity and mortality than chronological age again. So it was in 2013 with that first publication that we really sort of entered the era of, being able to assess biological age.
Got it. And since the initial Horvath clock, I think there's been a few other iterations.
Yeah, there's second generation and maybe even third generations. Yeah, that might be more predictive. I mean, it's a really interesting and an evolving field. So we will be telling age of different tissues. So, liver age, brain age, et cetera. Telomere, even DNA methylation of telomeres, which were the marker for biological age once upon a time, but they've since been supplanted by this science. We can look at morbidity, or even there's a clock called the Grimm age, which predicts mortality, better than chronological age by a lot. So yeah, we're really sort of busting into this new era and continuing to refine and evolve. So it's very exciting.
It's really exciting. I know that you wear a continuous glucose monitor because I've heard you talk about it. I wear one too. It's been fascinating and very, the risk is that one can become neurotic or
that's right.
Neurotic. You talk about that, and we can maybe later explore that whole idea of, I think you called it orthorexia, which is a whole interesting, kind of when you become a little too neurotic about your own health. But I'm sure that there are people working on developing what would be the equivalent of a continuous glucose monitor for DNA methylation age. And that's going to be incredible to be able to see on a snapshot, moment to moment or hour by hour basis, kind of, how your mechanism, how this pattern of energy here is interacting with its environment across, stress and food and toxins and all this. So I want to move back to DNA methylation because I want to make sure that this is very, very clear to everybody listening, because it's so foundational to what we're going to talk about and to your work. So I think we need to go even upstream from there and do some biology 101. So go back to DNA and what are the primary function of DNA. So do you want to take a swing at that?
Sure.
We can collaborate on it.
Yeah. So in the nucleus, in the middle of our, the little nucleal compartment in the middle of our cell houses our DNA, which is, comprised of just 4 bases. And these guys form genes, and we've got about 23,000 or so. And just a minority of those will go on to make proteins. So genes code for the various proteins that grow us, that enable us to make cells and enzymes and, tissue and, and on and on, hair, nails, just all of us, all of who we are is coded into our DNA. Whether a particular gene is on or not is dependent on the cell type, the needs of the cell, and is regulated again by all of the biochemical marks that are happening at the epigenetic level. So certain genes will be on, certain genes will not be on. So I guess I could give you an example. So the DNA is consistent throughout our body, regardless of the cell type. In a liver cell, the region of DNA that will be turned on is associated with the needs of the liver cell. A retinal cell, likewise, you don't need the genes associated with liver function to be turned on in the retina. And so those are hypermethylated and shut down. Brain cell different. So our cells specialize, even though we have the same DNA, what we allow to be turned on and what's shut down consistently varies from cell type to cell type. And that's done via epigenetics. I guess I'm probably going to get a little bit confusing here, but so some epigenetic changes. So some DNA methylation isn't going to change cell division after cell division. That particular gene is always going to be shut down. A liver cell will not become a retinal cell, no matter, how much you mess with yourself. Thank God. But as we'll get to, what the biological age clocks show and what my research shows is that there are labile regions of the epigenome, things that we can turn on and off through our lifestyle choices. And I know we're going to drill down. So that's perhaps a little bit more complex of a intro.
No, that's fantastic. So
okay, good.
So DNA essentially encodes or holds the recipes or the transcriptions for what our cells make. So like you said, it encodes for hormones like insulin or transport molecules like hemoglobin or neurotransmitters like serotonin, etc.
Yes.
And the epigenome is essentially the on-off mechanisms of those particular genes. And
that's right.
And that can change in response to a whole host of environmental factors, which you will outline for better or worse. And DNA methylation is essentially this kind of lollipop looking thing that's carbon and the 3 hydrogens that can connect to different DNA groups to essentially regulate that on and off switch. Is that a fair understanding?
Yeah, I think that's reasonable. So it's able, that red lollipop will bind to one of those 4 bases, actually cytosine, when it's sitting next to a guanine. And just visualize these red lollipops dotting that gene. You can just see a bunch of them sort of sticking up in the air. That's how they are denoted in the scientific literature. And it inhibits, you can visualize, it's interrupting a transcription factor from being able to get in there and, and access the gene. So it's just blocking, it's not able to
Right.
open. So it's simply a structural change.
So when a gene is methylated or
Mm-hmm.
hypermethylated, its
Mm-hmm.
expression is essentially inhibited, right?
Correct. Yep. By and
Got it.
large, that's the case. Yes.
So like let's pick a gene like the BDNF gene, which
Mm-hmm.
is a relatively celebrated gene
Yes.
that has associated with neurotropic factor, I believe.
Yes.
So when the BDNF gene gets hypermethylated, what happens?
Yeah, it's not able to be efficiently turned on. So there's a
Got it.
continuum. It may be, partially accessible. It may not be accessible at all. And it may be the BDNF receptor. So maybe you can make BDNF, but the BDNF receptor gene is methylated, inhibited. And indeed, that has been associated with problems. So they've studied hypermethylation of BDNF, and yeah, it's associated with stress and dementia and depression and so forth. Mm-hmm.
Right. And there's obviously many, many other genes. Like you
Yes.
talk at great length in the book about the tumor suppressor genes, for example. So like BRCA,
Mm-hmm.
that's also a gene that can
Yes.
be hypermethylated when you have methylation imbalance. Is that right?
Yeah. And it's not just methylation imbalances. When you have imbalances, maybe, it's so much beyond, it's much greater than just if somebody listening is familiar with the methylation cycle and you're taking your B12 and your folate, what we're talking about really zooms out beyond this. There are many more inputs that influence methylation than just B12 and folate. So again, going back to what you said, stress, lifestyle factors, adequate sleep, exercise, etc. Your diet above and beyond whether you're eating methyl donors. So many variables will influence the methylation patterns on our genes for better or for worse. And what's interesting about BRCA, so we know, Angelina Jolie brought it to prominence when, she talked about her mom dying of ovarian cancer, I think, when she was really quite young, and she, being a BRCA carrier, had prophylactic hysterectomy and mastectomy, and the minority of cancers are associated with BRCA. The minority of hormone-sensitive cancers, really a relatively small minority. What hasn't been understood as much is that we can inhibit BRCA, we can hypermethylate it, and
Mm.
therefore increase our risks. It's like our body is, or it's like it has the mutation, and we're just starting to kind of wrap our arms around this. Probably will be doing this in clinic. Actually, Illumina, the lab that we used for our research study and is a massive research lab, reference lab, has a test called the GRAIL test that looks far and wide at methylation patterns. Probably BRCA is in there and is able to give, risk predictions around cancer. So this is something that we'll be using, I think, in routine medicine. I think it's just a matter of time. The price point needs to drop, but these are incredibly important tools. And yes, let me just tell you this, actually, the aging journey causes hypermethylation of these tumor suppressor genes. So it's not just cancer
Mm.
itself. And
Mm.
that was a big aha for me, because I entered into thinking about epigenetics from the angle of thinking about cancer. And to see that some of the changes that happen in the cancer microenvironment look just like aging was revelatory, and really, I think, illustrates why changing biological age can so potently influence, other diseases.
Now, can you identify with specificity what environmental inputs actually hypermethylate BRCA, for example? Or is it
Um,
or is that too broad? I mean, we can't necessarily say, oh no, it's that, or it's that trauma, or that food, or that stress.
Yeah, we're not at that level of granular detail. That's right.
Yeah.
But we can, I think, we can know that we can know more broadly the negative inputs that will sort of wonk out in a more general way. And really what we tried to include in our research study was our read on the literature on how you can support things happening optimally. And there's like phenotypic differences. So this phenotype is what we end up looking like. So genotype is gene expression, what's on and not, and then how that expresses and how it looks is phenotype. And so our phenotypic expression, like the things that what I hypermethylate in my body perhaps could be different than, the imbalances that are going to show up in your body. Mm-hmm. But in general, I will say on the aging journey, we start hypermethylating tumor suppressor genes and other genes that we want on, our antioxidant genes, when we actually start to turn on our pro-inflammatory genes. In fact, it's so consistent, the patterns in the aging journey, that you can't help but wonder whether or not there's some program, that this is not just chance, this is not just living in a toxic world. Something appears to be regulating it because it's really quite consistent.
Yeah. And I mean, that brings up I suppose, a broader philosophical or spiritual question of, whether or not essentially we are predetermined to age and die on some level, that whatever foundational intelligence of the cosmic universe there is out there, we have it's adaptive from an evolutionary standpoint, that we become methylated at a certain point after a full life and pass away. Yeah. And I think what you're saying is that, yeah, that may be true. However, I think what you dub it epigenetic drift, that, by adopting certain protocols, we can slow that epigenetic drift without, yes, having to pursue this quest of immortality, for example.
That's right. And that's going back to James Free's work. That's right. Yeah, absolutely. I think it's an imperative. I mean, right now we're beholden to sort of the standard American vision, and we're surrounded by, and exposed to excess toxins and, damaged environment, et cetera, poor relationships, high stress. Like right now, we're pushing the aging program faster. In fact, that's what research suggests, that we're biologically aging faster. As you pointed out in the very beginning, our lifespan is cutting back and has been added to with COVID. But when we look at the biological age in this country, we see that we're actually aging faster. So our health span is being truncated along with our lifespan. And I think it's our imperative. I think we absolutely, if we want to survive as a country, and not bankrupt ourselves, we unequivocally have to be thinking about this. I don't, I think that's our spiritual imperative. And then beyond that, what do they call escape velocity, where you're like immortal? That's a whole nother conversation. It's kind of interesting, and I have some thoughts around it, but it's a different kettle of fish.
Yeah. I mean, I think one thing that's interesting is, like, you point out this delta, this 16-year delta of gradual decline.
Yeah.
And I think that's really influenced how we perceive elders. Now we think of elders as the elderly, and they're often, shipped off to some home. And oftentimes they're sort of defined within these parentheses of a burden, where, typically throughout history, the elders were seen as these founts of wisdom and
Yes.
knowledge. I mean, I think of like Lao Tzu, the father of
Yes.
Taoism. He's always portrayed with this wizened, with this long white beard. Actually, it's
Yeah.
fabled that he was born with the beard. But anyways, but it's and that, but we have this decline, I think, has really changed how we think about our elders. And it's
Yeah.
very sad, actually.
Yes. Yep.
So I wonder, is there a metric for measuring methylation specifically? Is there like a compound that shows up as some kind of biomarker?
Oh, yeah. I mean, we're able to
Yeah.
measure what they call the methylome, which is the entire pattern of DNA methylation. Yes, and that's what we used again, going to Illumina, we used a assay in our research study to be able to do that. Yes. So you can, in fact, look at methylation and look at methylation changes very sensitively these days.
And is that what is homocysteine? Is that a marker for it?
So this is different. So I'm specifically talking about the DNA methylation. For us to make that red lollipop, the carbon and 3 hydrogens that gets put on our DNA, and let me say, we use methylation in every aspect of physiology all of the time. So methylation is happening everywhere, doing all sorts of stuff. My focus is DNA methylation, but we use methyl groups to clear out, to transform compounds. Like if you want to make adrenaline or if you want to make dopamine, you use methylation. And conversely, if you want to metabolize that adrenaline out of the body, we use methylation. We use it to transform estrogen, to make it into a less active compound. What else? We make, neurotransmitters in brain health and, and motor neuron neurotransmitters, et cetera, all use methylation. We make certain fatty acids. I mean, sort of on and on and on methylation. It's happening in the mitochondria and so forth. So we have a methylation cycle that makes these methyl groups. So the methyl groups are carried around the body and used in these methyltransferase reactions. We've got, almost 400 of these methyltransferase enzymes, DNA methylation just being one methyltransferase type. And we make them in the methylation cycle. We produce a compound that people have probably heard of. It's called S-adenosylmethionine, or SAM. Some people call it SAM-E, same compound. And we make it in the methylation cycle, and we're pumping it out all the time. And this methylation cycle sort of uses it and then recycles it and then uses it and then recycles it. And S-adenosylmethionine then leaves the cycle and is used in these various methyltransferase reactions all over the body, all of the time, and puts methyl groups, on where the enzyme dictates. So, back to homocysteine. When we spend that methyl group, so when we take the SAMe and we use it, it becomes S-adenosyl homocysteine, and then it's converted to homocysteine, and then it's recycled back up to methionine, and then it becomes S-adenosyl methionine again. So in the cycle, homocysteine is a fundamental and important player in regenerating spent SAM. So homocysteine has been used for many years as a marker of cardiovascular disease risk, and it is associated with it. It also, when we see it very high, or maybe even very low, but particularly when it's very high, it has been associated with less effective global methylation. So as we age, homocysteine rises, and as we age, methylation happening body-wide and on the DNA is less efficient. So I would say, Jeff, homocysteine is a loose surrogate marker of methylation. So if it's very high, we can say, yeah, methylation is wonky in this individual, and we want to be thinking about it. We need to be mindful around drawing too many conclusions beyond that.
Yeah. And I'm glad that within that commentary, you were clear about the notion that methylation isn't really all bad. It's like what we're looking for is the Goldilocks zone of
Yes.
we want some genes turned off and we want some gene expression turned on.
Yes.
And it's about actually finding that balance, that Goldilocks zone with methylation. No one should be under the delusion that methylation is a bad thing. As you said, it's protein. It's happening all the time, everywhere, omnipresent.
Oh yeah, it's essential. We need functioning. Yeah. We need very high function. We want to keep methylation whirring along as effectively as possible. When we look at DNA, so it's just very interesting because it's a U curve. We want it to be happening at the right place in the right amount. When we age, so when we look at age, when we look at DNA methylation as we age globally, so if you measure all of the DNA methylation in a given cell, you'll see that we tend to methylate less effectively. So our quantities drop. But you don't just want to turn the volume up on methylation, because when you zero in on different genes, you'll see that hypermethylation is happening. So there may be a global decrease, but there's also an imbalance. So again, antioxidants, anti-inflammatory genes are shut down. Tumor suppressor genes are shut down. Pro-inflammatory genes are turned on. And it's this imbalance that we really want to think about correcting. If it were just a matter of turning the volume up on methylation, we could all take a bunch of B12 and a bunch of folate, and live forever. But there's, it's just a little bit more nuanced than that's quite a bit more nuanced than that.
Let's specifically dive into your clinical trial to explain kind of how you tested some of your theories about reducing biological age. Do you mind spending some time talking about the nature of that trial and how you organized it, and then some of the results that you were able to find?
Yeah. So around maybe 2013, 2014, I'd give you a little bit of the backstory. Again, interrupt me. I was reading the literature on epigenetics. A lot of it coming out at that time was related to cancer, and again, cancer very efficiently takes over our epigenetics. It takes over our gene expression, turns genes on for its own survival, turns genes off for its own proliferation. I mean, it's like a bad deal. And it occurred to me, so being a functional medicine physician, the big question was how might we be influencing this? Are our treatments helping to optimize DNA methylation? At that time, I did not know about biological aging. So I entered into it through the lens of cancer. And we ultimately decided in my clinic, I've got a extraordinary team here, and my friend and colleague Romilly Hodges, who started our nutrition programs, she and I decided to build a program to optimize DNA methylation, what we thought would. And so we went headlong into the literature, looking at all of the variables that negatively or favorably influence DNA methylation, and ultimately designed the methylation diet and lifestyle program. And we started to use it here in clinical practice. I published it on my website just as a basic ebook. It was written for professionals. I actually lectured on it. So in functional medicine, they were really kind of interested. And I, lectured on it in South Africa and Ireland, actually Cleveland Clinic. Mark was interested in this, Mark Hyman, very early on. And he wanted his team over at the Cleveland Clinic to understand what we were doing. So exercise, sleep hygiene, meditation practices, some basic supplements of, just a probiotic and a greens powder, and a very specific diet. This diet is heavy in methyl donors, so lots of leafy greens, nuts and seeds, good fats, mushrooms, etc., eggs, some animal protein. Heavy in methyl donors, because remember, as I said earlier, we don't methylate as well as we age. So we wanted to pack them in there. But also very rich in these in phytochemicals, in polyphenols. Polyphenols don't participate in that methylation cycle I've been talking about, but they do influence how methylation happens at DNA. They seem to direct methylation to occur in more favorable patterns. And so you brought up the tumor suppressor genes. There's what I think is one of the coolest parts of the book is this table that I constructed that shows different genes that can become hypermethylated, different tumor suppressor genes, and the evidence for the various phytochemicals that will restore activation of these tumor suppressor genes. And so you can look at, nutrients that you can take or food sources that you can get. We have a nutrient appendix that outlines all of these nutrients. So the whole program is designed around optimizing gene expression. We were granted an unrestricted grant. Actually, we're given an unrestricted grant from Metagenics to study it. So we wanted to look at it. And, to your point, outside in the clinic setting, we would have been able to measure homocysteine. We would have been able to do some very basic measurements that wouldn't really tell us what was happening with regard to DNA methylation. And so it was just sort of a rather extraordinary miracle that Metagenics came on board. Brent Eck is their CEO, and he's a good friend of mine and was compelled by the work we were doing. And so he funded it, and we were able to use the kits that assess the whole methylome in the research setting. So the leap from thinking about cancer to more broadly thinking about nutritional epigenetics, so nutrients and lifestyle impact on gene expression, was a natural leap. And then as I evolved, just my understanding in epigenetics evolved, I began to piece together the extraordinary fact that aging at the level of the epigenome looks like these diseases, and and sort of most correlative is cancer. And so our program is just by the fact that we're addressing epigenetics, a rather extraordinary anti-aging tool because of the shared underlying biochemical mechanisms. And so that became the first analysis that we conducted, and it was the first study of its kind to show a biological age reversal of over 3 years in our participants as compared to the control group in 8 weeks time. It hasn't been demonstrated. Again, there's been some other modest bioage reversal studies to come out, and there was one that preceded it, which was a year-long intervention. But really, it's new. It's just really profoundly new. Yeah.
Well, we hear so much about, cellular pathways like the sirtuins or mTOR or AMPK, et cetera. But most of those studies really have been done either with yeast or,
Right.
or, in
Mice.
vivo with mice, so we haven't really seen, human studies, en masse. And so can you take us through, how you ran your study specifically? What were some of the protocols that you administered, and how long did the study run for? Was there a placebo group, et cetera, and some of the conclusions you mentioned already?
Yep.
But yeah.
So link to the paper if you can, and link to the book. So the book will really hold your hand through it. We actually have an app where we're continuing to study. So remind me, Jeff, to tell you about some of our preliminary findings that I'll be writing up soon. So the app will completely hold your hand. The book will partially hold your hand, and then you can read the paper, which is written in relatively plain language, and it has the protocol, and it's the full text is free. It's open source. So it's a 8-week program. The diet is very plant forward. You'll be eating about 9 cups of vegetables per day, most of those greens. We've got a variety of gene whispering foods that we think one needs to be consuming with regularity. So beets, eggs, liver. Liver is such a dense gene whisperer. You don't need to have it every day, maybe 3 servings a week. Again, a bunch of greens. Mushrooms are extraordinarily potent in important, methylation associated nutrients. So shiitake is one of our favorites. Green tea, curcumin, seeds like pumpkin, sunflower, good healthy fats. You can do a little bit of medium chain triglycerides or, fresh fatty fish. So no, I don't think any of the elements in the diet would surprise, somebody who's got a healthy eating pattern. The quantities and the fact that we lean on beets and some eggs and so there are some unique components to it, but it is a healthy eating pattern. Mild intermittent fasting, so nothing, or time restricted eating, so 12 hours on, 12 hours off. It's very low glycemic. It's very low hypoallergenic and low inflammatory. No grain, no legumes, no dairy in the first 8 weeks. I'm a fan of legumes, so people transition into it after, but just in this first 8 weeks, we really wanted to control glycemic cycling and minimize any negative reaction. So, a lot of people react to beans just with GI distress. And so we just pulled them out for that first 8 weeks, but for anybody out there who's thinking I'm anti-bean, I'm not. It's keto leaning. So we saw our subjects drop triglycerides. Triglycerides, when we're in ketosis, we're burning a lot of those fats, and our participants reduced their triglycerides by, a significant amount. And so they were probably in ketosis. And so that's the basics of the diet. Good hydration. We didn't insist that our participants eat organic. Obviously, if you can eat organic, that's fabulous. But it's nice to see we got these results without insisting on organic, because it just makes it more broadly attainable to a variety of income levels.
Yeah, obviously not as nutrient available, perhaps in non-organic, given the
That's
nature
right.
of glyphosate and its chelating
Yes.
capabilities and all that kind of stuff. But that's a whole nother.
Well, there's no doubt.
But, yeah.
If you can do organic, do it. I mean, there's just no doubt about it. But it's also nice to have it available when, organic isn't.
So you administered this this protocol, this diet, for 8 weeks, and I assume that you were running BioAge.
Yes.
On either kind of throughout the whole process or just kind of at the beginning.
We did a baseline. So we did a baseline, midway, and then final. We certainly didn't need to do a midway. There was no significant change in midway. Maybe there was a slight trend towards lower BioAge, but yeah, we did it at baseline and final. Yeah. Really important in our study, and we got some we got some other standard measurements, some standard chemistries, lipids, and so forth. We measured folate. We measured other methylation. So we looked at homocysteine and some of the other methylation cycle markers. So we looked at a host of different stuff at baseline and then at the end. We had our participants work with our nutrition team. Each participant was required to meet with a nutritionist at least weekly, more if they wanted to, and for at least the first month. If I was going to point my finger towards one success factor, this is a complicated intervention, and leaning on our nutritionists, I think, was the difference between success and failure. We did get adherence data on our participants, and we can see that they did a good job. It's quite extraordinary. In fact, my co-PI, who is the director at Health Gut Institute, and that was the clinical research center we hired to run our study. He was studying us to see how successful we would be because it was a really complex intervention. And knowing that I'm probably not going to be handed another unrestricted grant like this, I really wanted good adherence. And so having our nutritionists right in there in lockstep with the participants made a huge difference.
Yeah. And so I think it's worth mentioning that this first study was focused on males, right? Because there were just too many confounding variables with women and menopause and hormones.
Yeah.
For this one, right?
That's right. So we wanted to look at when methylation gets wonky, basically. I keep saying, as we age, it changes. It really kind of deteriorates. And so we wanted to look right in the sweet spot of when that starts to happen. And so we included men aged 50 to 72 in our study population. Women in that age range would be anywhere from peri to post-menopause. And our numbers, our study numbers, it's a pilot study, so the numbers are low because it was expensive. And if we had the confounding variable of different hormonal changes, that would have been difficult for us to gauge response and sort of tease out the hormonal influence. But I want to say, to your point, Jeff, that we have a small cohort of women who've just finished in our app within the same, I think, within the same demographic, so in the same age category, and they did fabulous. I mean, I can't wait to write it up. They actually did better than the men did in our research study, although we used a slightly different clock. So it's not apples to apples comparison, but it's really exciting for me to be able to say, women rocked it. And I've been measuring my biological age for a long time, and I've been doing this program for a while. So I've seen my favorable N of 1 changes, but it looks like, women are as responsive and maybe a little bit more than men.
Amazing. And remind us, what did you see in the end in terms of biological age reduction in the participant group?
And I want to circle back and talk about the lifestyle pieces as well. As compared to controls, our study participants were 3.24 years younger. When we compared them to themselves, so where they were at their biological age at start versus finish, they were 2 years younger.
Amazing.
Yeah, it's absolutely amazing in 8 weeks' time.
Right?
Yeah. Yeah.
And it's so exciting because it also shows how sensitive the body is, and how, if it's well nurtured, it really wants to heal. It really wants to be thriving and not just surviving. And it's amazing that you were able to accomplish that over 8 weeks.
One of the really cool things to me is one of the coolest is that when we look at the other methylation data that we gathered, so homocysteine, S-adenosine methionine, et cetera, we did not appreciably change that. So our participants were healthy, and that's an important point. People who are sick, so if we had done this study in diabetics, they're going to be biologically older. So all of these chronic diseases of aging are associated with biologically older ages. And if you reverse the diabetes, you will you'll slow biological aging or reverse that. So your average diabetic is maybe 6 to 8 years biologically older than, a non-diabetic counterpart. But we were looking at healthy guys. So they didn't have high homocysteine. They didn't have high blood sugar, et cetera, et cetera. So we didn't appreciably change those methylation markers. What it looks like we did is rearrange where methylation is happening on the genes to a more healthy and more youthful pattern. So we moved those lollipops around, which I just think is so compelling and really interesting. And we actually still, Jeff, have more data to investigate and publish on. So going back to hypermethylation of tumor suppressor genes, I can see that we changed methylation status in the promoter region of our study participants considerably. And that's something that I'd like to get into and sort of tease out a little bit more and write it up.
Yeah. Were you looking at other biomarkers across this time too, like fasting insulin or CRP or triglycerides, LDL, et cetera?
So we looked at triglycerides, and we dropped our triglycerides in our participants significantly. And that to me suggests that they were probably in a little bit of ketosis. We dropped their total cholesterol as well significantly. LDL in our study participants as compared to baseline dropped. But we didn't change other markers. Now remember, they're healthy. We didn't measure fasting insulin, blood sugar. We did a standard chemistry. Nothing appreciably changed there. So yeah, we increased folate. So we increased methylfolate. No B vitamins anywhere. No folate fortified foods were allowed. So naturally, with the diet and lifestyle interventions, we increased circulating methylfolate significantly in our participants. So bioage as measured by DNA methylation, triglycerides, cholesterol, and folate were the markers that we saw change.
Got it. So if I'm understanding correctly, you're essentially saying that methylation patterns are nutrient sensitive. Is that a fair understanding?
Yeah, I think so. And I want to say again, it's a continuum. So like I said earlier, you're not going to turn a liver cell into a skin cell, and you don't want to. You want those methylation patterns to be rigorous. You don't want them going anywhere. Oh no. Stop. But there are these regions of sort of more changeable, more environmentally responsive, DNA methylation patterns. And yes, I've termed them nutrient responsive genes, and we're just tapping this area. We'll be looking at it, for hopefully years and years to come. But yes, there are nutrient and lifestyle responsive. So not even just nutrient. Let me tell you this wild factoid. I need to talk about the lifestyle factors, but exercise, which we prescribed in our study, behaves like those phytochemicals that allow tumor suppressor genes to get turned back on. Like exercise acts like a vegetable when you look at the epigenome.
So
which I just think is so cool.
Yeah. So break that down a little bit in terms of the type of exercise, because I think there is some debate right now around, high intensity interval training or more like zone 2 exercise. What were you prescribing, and what is your current understanding of what the appropriate kind of exercise is that we should be getting?
Yeah, good question. So we needed this program had to be doable. In fact, one of our reviewers, when we published, commented on that, the fact that this is a doable program. You can't do a drill down into really sort of elite kind of very individualized prescriptions in, a randomized control trial like this. I mean, you can, I think, if you have endless funding, but it's challenging and it's difficult to repeat, etc. So we just prescribed a very foundational exercise pattern, 30 minutes minimum, 5 days a week. 30 minutes minimum, 5 days a week. Perceived exertion, 60 to 80% of max. Do whatever you want. So 30 minutes, 5 days a week was it. Perceived exertion up to 80%. That might be walking, a little bit briskly. I mean, my 80% perceived exertion is going to be different than yours. Some of the guys in our study, these were healthy men. Some of them had to dial it back for this study time period because we prescribed such a modest intervention. Some of the guys walked to work, maybe walked the dog a little extra. Some of them, gardened or cleaned or biked or whatever. But we wanted it to just be simple and doable. In the book, I talk more broadly about exercise. Yeah, I think, there's good evidence around zone 2. There's amazing evidence around high intensity interval training. I would say in general, there's good evidence in resistance training. As Morgan Levine says, exercise is anti-aging pill, basically. I mean, it's like one of the most important interventions we can do. I think a precise prescription will for each of us. So I think we're going to find individualized ideal prescriptions, and this will happen as we're able to measure biological age more readily. So what's my sweet spot? It's going to be different than what your sweet spot is, but we know we want some muscle. We don't want to lose it all. We want some resistance training, super essential, and we can see that favorably influences DNA methylation. High intensity interval training seems to be useful for a variety of indications, and certainly reducing risk for all of the chronic diseases of aging. I think that the most important is a consistent pattern of doing something that you love. What else do I want to say about exercise? There's some evidence that overdoing it is a pro-aging phenomena. So that's in the literature, and, specifically relating to DNA methylation changes. So over-exercising, and anybody who's ever, been a competitive athlete, like I was a cyclist in college, I was a competitive cyclist, and, at the end of the season, I always got sick, I always had a round of sinusitis, and you can measure the changes in immune response after a season of, high athletics. You're a little bit immunosuppressed, you're vulnerable to getting sick. So there's over-exercise that we want to avoid. Or at least just do for a finite time. I wouldn't change my competitive years for anything because it was so fun. But I don't know that it's a life-extending thing to do.
Yeah. No, I think that a lot of people talk about hormesis, or the hormetic response, essentially. What won't kill you makes you stronger. So, short bursts of oxidative stress associated with high intensity workouts. There's plenty of people in that camp. But I think, as you say, you can overdo it, certainly in times when I was a competitive tennis player, and there would be like weeks where I would just be sore, because of lactic acid buildup, because I was in sort of mild hypoxia all the time because I was working out so much.
Yeah.
And I kind of sacrificed my aerobic cellular respiration for, fermentation or whatever that would produce lactic acid and just and I was walking around, I was sore all the time.
Right.
And that was no fun.
Right.
So it seems like there is like a middle ground, particularly as we get older. I mean, I'm 51 and sometimes I still play tennis. And when I get out there, I think I'm 26 and I'm very quickly reminded that I'm not. But I think, as I get a little bit, wiser, as you say in the book, as my potato gets a little cleaner, which is a Zen training. I've become more moderate. I do some resistance training. I do some hiking. I'll get my my heart rate up, a few times a week, but
Good.
It's certainly not like something that I'm doing
that
all
you
the
used
time.
to do.
I am doing quite a bit of time restricted eating, so I'd like to talk about that component of the protocol. And I guess I'll also just say that in the book, the protocol is laid out for people who are interested in going through it and sort of self-administering it.
Yes.
And I want to get into some of the self-administered tests or assessments that you have in there, because I took it and I want to brag.
Cool.
I want to just prod you for a moment about your thoughts around time restricted eating. How severe does it really need to be to get the results that we want, etc.
I did not want this to be a study about time restricted eating. I mean, there's plenty of those going. And again, I wanted this to be broadly adaptable. I wanted, like, my avatar was like Marge and Boca Raton. I remember talking early on. Like, I just want anyone, or my mom, who I quote in the acknowledgement, saying she's doing it because methylation is good for you. Like, I want anyone. It's so funny. I just want anyone to be able to do this. And a 12-hour window is doable. Like, it's just really broadly doable. Do I think, and certainly Walter Longo would argue that it's where we want it to be, around 12 hours. But then there's plenty of other folks. Of course, David Sinclair is a large spokesperson for a more severe time-restricted structure. I think he's eating 2 hour. He has a 2-hour feed window. So for me, that would be very triggering, right? I mean, if I had a 2-hour eating window, I mean, and I heard him on a podcast say that he goes out to eat. I would be eating a king's feast, at that meal. I wouldn't be making sane choices. I wouldn't be having 9 cups of greens with my beets and liver, And so for me personally, that would be triggering. I think for women in general, we need our structure. We need to be really respectful of our bodies and actually, and men as well, but it will show up differently. So I think the research on time-restricted eating, on some caloric restriction, I mean, I think it's one of our most potent tools. We all have to look at what works for us. The best evidence we're going to get for a structure working is that we feel good, that our biochemical markers, that, our lab values are within, optimal range. And I actually include some of those in the book. And then hopefully we're getting biological age. We're able to get biological age, or, you can use the quiz, as you're going to talk about in my book, to get feedback that we're in the right direction, that we're doing something that works for us. When you're a pretty severe restrictor, you'll lose those benefits if you fall off of it. And so it's something that you really want to be able to maintain for the long haul. That's true for any of these interventions. We know from the literature that we can get favorable changes to DNA methylation sometimes with just one activity. But it's, the daily engagement in eating for or living for our, optimal gene expression that's really going to make the biggest difference.
Yeah, I think you make such a great point around how this cannot be seen as a diet. It really just needs to be seen as a lifestyle, because diets are almost framed to fail, or at least to end.
Yeah.
And then where are you? And so much about kind of a healthy epigenome is progressive. It has to be consistent. It's just about the way that you live your life.
Yes.
And
And when we think about it, so just, going down to the molecular level or the biochemical level, when DNA, so when a cell divides, the DNA also is dividing, and that's a key time that we can sort of reshape what's happening with regard to methylation. So DNA methylation marks are going to be placed back down or not. And so it's cell division over cell division over cell division over cell division that we can transform what's happening at the level of the epigenome. So we want to just kind of settle in for the long haul. And that means that I think one of the ways we can use this book, I would say all of us should do our 8-week intervention. But if you're not ready, there's plenty other to do in the book. I mean, one of my most favorite parts of it, in addition to the tumor suppressor phytochemical table, is the nutrient appendix. There's hundreds, maybe thousands of nutrients that influence gene expression favorably. And I list as many as I was able to find in the literature at the time of this printing. Anybody, the most picky eater, the most resistant, the most standard American diet driven individual will look in there and find some nutrients that they like. And so maybe that's your entry point into this conversation, and you can expand from there. So, it's broadly adoptable. It can meet people where they're at.
I'd like to talk a little bit about community for a moment. Now, I remember before COVID came along, Vivek Murthy, who was the Surgeon General for Obama, and I believe he's the Surgeon General again, he made a statement that loneliness is our biggest epidemic.
Right.
And I'm interested in probing a little bit around the nature of community versus loneliness, and how that actually might be connected to biochemical mechanism. I mean, are those factors in methylation, for example?
So we know that trauma will change DNA methylation. We know that we can inherit trauma from previous generations that will show up as changed DNA methylation. Depression, post-traumatic stress, early life challenging events. So this is when psychic experience is sort of translated into biochemistry. You can it's extraordinary. So you can dictate genes on or off. Psychic experience is translated into biochemical marks that then influence patterns of genes, and both with regard to again, going back to BDNF or oxytocin, the love hormone, or genes related to inflammation or metabolic disease, etc. So these negative psychic experiences can influence gene expression to increase risk of a disease, to increase inflammation, and also to drop how we feel, to change how we feel. In fact, there's one study that I talked about in the book where just perseverating, just sort of being locked into the negative loop could be hinged in epigenetic changes. And I think also sort of allowing ourselves to stay in a negative loop could really change epigenetics. So epigenetics could change us, and our behavior can also change epigenetic expression. So to that end, I would say that loneliness would absolutely negatively influence epigenetics. And we can look at community and the ability to increase production of, the love hormone, oxytocin, et cetera, cuddling, connection, community. And those positive influences are certainly associated with longevity and with reduced risk of the diseases of aging and so forth. So conversely, yeah, I haven't read literature directly on loneliness, but I don't understand. I don't think that it would escape, having a negative influence.
Yeah, I would say loneliness or alienation, disconnection is a byproduct of trauma-inducing events. And I know that you reference I believe in the late 90s, there was a significant ice storm in
the Project Ice Storm.
I think it was in Montreal or in Quebec somewhere. And that caused a tremendous amount of duress for pregnant mothers. And then there was a downstream impact of that. Is that right?
Yeah. So, I mean, I think it caused a lot of stress for everybody, but they studied pregnant women. So they studied the offspring of pregnant women, and those women who experienced heightened stress, physical, so it's freezing and you have no power, etc. So there's a physical stress component, but also emotional. And there really wasn't a difference between the two. There was no difference. Gave birth to kids, most likely, with a higher incidence of autism and a higher incidence of allergies, of asthma specifically. So this is a stressful experience, physical and emotional, either or both, that changed epigenetic expression in offspring and increased disease risk.
Right. We'll pull on that thread a little bit more in terms of meditation, restoration, relaxation, sleep. What are some of your protocols around those areas?
So stress is pro-aging, is potently pro-aging. And we can see that stress changes DNA methylation. So to your point, loneliness can be profoundly stressful. So that could be another angle one might look at it. But yeah, so we can see stress as potently pro-aging. I articulate it in the book as being like gasoline on the fire of aging. In the particular clock we used, 25% of those methylation sites were influenced by glucocorticoids, by cortisol, the stress hormone. which to me just shows how extraordinarily potent stress is on biological aging. Conversely, when you look in the literature on, contemplative practices or centering practices, so meditation, yoga, tai chi, etc., they are potently anti-aging. And you see folks who are practiced meditators, they are biologically younger. And there was a really interesting study looking at biological age in cardiovascular disease. I think they had a healthy population, and then they had heart disease patients. And the healthy population, and not the heart disease, and it would be interesting to sort of figure out why. I don't know the answer to that, but they got younger using a meditation practice. Beyond that, we see that it doesn't take a lot. You can see favorable changes to DNA methylation, so favorable gene expression changes with just one practice. But lasting anti-aging changes happen with a regular contemplative practice. It's just really cool. So you start the journey, and you're going to get benefits right up front. They show that with exercise as well. Stick with the journey, and the dividends, the rewards increase.
Yeah. Now, obviously, developing a meditation practice has myriad knock-on beneficial impacts. Methylation was a new one for me, but obviously, the growth of additional gray matter never hurts, or, essentially being able to move yourself, out of your sympathetic nervous system and into a rest and digest or parasympathetic state to be able to essentially control neuromodulators like cortisol. And of course, the world at this juncture feels to be amygdala hijacked and in a constant place of cortisol infusion. And that is really mortgaging our ability to leverage our prefrontal cortex to have rational conversation and, our ability to cooperate with each other. But then all these other downstream impacts around dysbiosis in the gut, which can lead to intestinal permeability, which can lead to, chronic inflammation, or, blood glucose spikes, which can lead to glycation and advanced, these ages that can, gum up essentially your vascular system and lead to cardiovascular disease. So there's every reason in the world to adopt a meditation practice. Of course, it also is provides a very different kind of way to experience yourself too. So we don't need to probably cheerlead anymore for meditation. There's so many reasons to do it.
And get younger if you do need a motivation.
And get younger. Yeah. I mean, so
well, let me say this. I want to just add this. We may be getting there in our podcast, but as we start to get closer to sort of cracking what causes aging, there is research emerging that really suggests that the most root cause may be DNA methylation and epigenetic changes. And so going to this source and working from this, thinking about gene expression. And I'm going back to meditation because this was our topic, but that may be like a root cause anti-aging intervention because you are favorably changing DNA methylation, and there is some evidence that that might be the crux of where aging begins. So all of these interventions, don't take them lightly. I mean, they're powerful and potentially just life altering.
Can you explain what adaptogens are?
Yeah, so these are the phytochemicals. Favorites include green tea, curcumin, luteolin, quercetin, fisetin, what else? Lutein, on and on, resveratrol, sulforaphane, diindolylmethane, on and on. These are the phytochemicals found in plants that seem to direct where DNA methylation is happening. That's how I explain it. So, again, going back to our findings, we didn't increase net DNA methylation in our participants as compared to controls. We rearranged how it was happening. And so our methyl donors kept methylation going. And these what we call methylation adaptogens, I think, directed where it happened towards a more favorable and youthful pattern. That's how I think of these methylation adaptogens. And there's tons and tons of them. We have our favorites, but there's so many. And in the nutrient appendix, I talk, endlessly about food sources for these extraordinary nutrients. Honestly, every forkful could be a gene whispering epinutrient. So both, we call them epinutrients at this point. So methyl donors or these methylation adaptogens, both influence epigenetic expression.
Epinutrients, I love it. So if someone wants to essentially avail themselves of the Younger You protocol and start to adopt this kind of this myriad of modalities and dietary choices around adaptogens and the low glycemic diet and sort of a quasi plant forward keto diet that you outlined, obviously exercise, restorative practices, sleep, one can also kind of self-assess and monitor their own progress around bioage as they go. Now, clearly, some of these more advanced bioage clocks are becoming more commercially available. But you have also designed a number of self-assessments where people can, just get a handle on in terms of where they are as they go through this protocol. Can you just talk a little bit about those?
Yeah, so we created what we call the BASA, Biological Age Subjective Assessment or Self-Assessment, and it's in the book. Yeah, so yes, if you can afford to get a biological age clock, do it. There's a list of labs that you can consider using in the book, and I would say to go for it if you can. But they are relatively cost prohibitive still, but you can do our biological age self-assessment, and this will give you an idea of your starting point. You can see what you're good at, you can see what you're struggling with, and you can just start to make your changes. And you can do it, midway. You can take it weekly. If I were starting my 8-week program for the first time, I would take the BASA every week and just see how I'm doing. And you'll see it change. It doesn't we purposely designed it so that it doesn't have a ton of wiggle room. You're not going to do our BASA and find yourself, being 20, but you'll definitely see some favorable shifts as you do our program. For me, I sit too much. I need to be over on that exercise desk over there, but I have my lighting set up here, and so it's just easier. Although now with my son coming in, it's not so great. But you'll be able to just look at it and see what you can improve, see what you're already doing right, etc. I think it's easy and it's fun and it's cheap. It's not validated. It's not scientifically validated, but we actually may be able to validate it over time as we collect more data in the app.
A lot of the things that you talk about, I think, in terms of the protocols, like eating well, sleeping well, moving, community, meditation, these modalities are what I call old and true. They've been essentially proven over millennia. Yeah. And now the beautiful thing now is now we can open up the hood of the car and actually look into empirical data around them. So that's new. Yeah. But there was a lot of intuition, even by the Buddha, 2,500 years ago, that meditation could be a salve from craving and Trishna and et cetera, and help us move towards a sense of nirvana or letting go. So, but kind of running alongside some of these older, more proven protocols is what I sort of consider the Wild West, the new frontiers of the longevity and biohacking movement, which encompasses a lot of very new science, new science that hasn't necessarily been able to undergo a lot of rigorous randomized clinical trials like yours, and that has spilled over into significant self-experimentation. So I want to just probe your opinions about this, and you do address this later on in the book, but what are your feelings about taking things like rapamycin or metformin, for example, as in the pursuit of longevity?
So I guess what I would say is that, I mean, so the individual who decides rapamycin is for them or metformin is for them, they still need to eat. They still need to sleep. I think this could form a foundational structure, and you can modify it. So using it in clinical practice, we've found these tools to be very modifiable to other dietary patterns. So you could do your 16-8 obviously and follow this, or somebody who's got IBS and is on a low FODMAP diet can still use these. So I would say that regardless of where you're falling on the biohacker continuum, these principles should still be incorporated. Like it's just a 100% no-brainer to me. There's been more attention these days to not eating and to the empty space and no food versus the nutrient density of when you're consuming food. I think hopefully that pendulum will balance out a little bit and we'll realize how much power we have in actually choosing the information on our fork to direct our body. I think we've lost sight of that in some ways lately. So I think that there's probably a place for rapamycin, much lower than what we use in transplant patients, and a small amount of it might be both healthy and health span promoting. I think the science is kind of leaning towards that. Metformin, so we know keeping blood sugar low, and metformin has other benefits beyond just lowering blood sugar. It might help with mitochondrial rejuvenation, but it's a bit of a toxin if you take it and you exercise. I mean, there's a lot of nuances to how to use metformin, and there's and that's probably true with rapamycin, like how and when you take it. And using metformin outside of diabetics, we just don't know. I mean, Nur Barzilai, if I'm saying his name right, I mean, he's at the front of researching this, he and his team, and they are looking at using it outside of diabetics. And, we just really need to pay attention to what he finds. So I guess what I would say is that if people, I'm a fan of leaning on some of these interventions if they're appropriate. If we all jump on them, or I know some folks are going higher and higher with rapamycin. I sort of follow a handful of those threads on Twitter. We're entering into just unknown territory. So there's a lot of self-experimentation going on. I mean, people are using the gene editing software CRISPR, and hoping that they edit out, the genes that promote disease, et cetera, or promote, a shortened lifespan, or, they're trying to manipulate longevity with gene editing. And that's just beyond, like, that's just really scary to me. It's pretty crazy. But you know what? I'm all for sort of a careful exploration of using hormone replacement if that's something that's appropriate for you. So and it doesn't need to be exclusive. The research that I cited earlier, looking at turning back skin cells, so a 50-plus-year-old skin cell back to a 20-something skin cell, or mice, old mice back to young mice. They did it in a age-related optic neuropathy, and these mice were blind, and then they changed epigenetic expression and they could see. I mean, and these were using transcription factors called Yamanaka factors. And so we know you can create youth by changing DNA methylation and demethylation. It's been shown in these cells in animal studies. It doesn't just automatically translate into humans. Humans are infinitely more complex than animals. But I'm paying attention to it. I think it's really interesting. And at the very end of the book, I ponder, and you brought this up earlier, Lao Tzu, like all of this wisdom. It's my expectation that, just like we might store trauma or store stress in our epigenome, that we're also storing our wisdom. It's showing up as DNA, methylation, these biochemical marks. And if we just turn back the hand of time with something aggressive like Yamanaka factors or, perhaps a high dose rapamycin or something, maybe, I don't know that, I think rapamycin's been studied long enough where it's probably not changing DNA, but these Yamanaka factors, I mean, would we risk like wiping free some of that wisdom that we've worked so hard at accumulating? I mean, I just think that's fascinating in this quest for youth. I mean, how is it that we would just sort of preserve muscle, maybe preserve brain size, preserve, youthful skin, et cetera, but not erase some of that, hard-won learning that we all go through, as we become clean potatoes?
Yeah, it brings up all sorts of really fascinating philosophical and ethical dilemmas and questions. Sometimes I think about kind of in this pursuit of immortality, if essentially, you could live forever, if you could figure out some technique that you could make any cell pluripotent, basically.
Yeah. Well, that's what Yamanaka factors do. Yeah.
Right. Would you ever go outside? Because the only way that you would die would be to get hit by a bus. So would you basically like start to live with so much fear because all of a sudden we've found all these keys to immortality? And it's very strange. I mean, I think it kind of goes back to the conversation that we prodded at earlier, is that, are humans essentially determined to die? And are we here for a particular time? And, as animated information, and to be here and to connect with everything around us, and then be part of this sort of continuous cycle of energy, and then pass the baton forward such that, asparagus and roses can grow in a field,
Yeah.
It gets a little, potentially overly poetic, but I do think that there is an ethical question around the nature of longevity, and I love the way that you approach it, because I think that by using these modalities and focusing on the things that are old and true, that they're more aligned with what it actually means to be human, instead of essentially trying to shunt some sort of artificial hack into what it's potentially into something that's not really human per se. And anyways, I think it's a fascinating, conversation, and I think it's one that's sort of playing out.
Yeah.
My only concern or worry is that there'll be so much momentum around things like CRISPR or Yamanaka that we skip over some of the more ethical and philosophical debates.
No doubt. Yeah, absolutely.
So,
I mean, it just seems like how humans roll, isn't it? We tend to
right.
just skip over that. Yeah, for sure.
Yeah.
I mean, I was reading one scientist's book. At the end of it was great. He got into the biochemistry of the kind of some of the work he's done. Howard Katcher, his name is. But in the beginning, it was all this exploration of like space travel, and we need to colonize Mars if we're going to live forever. We need to have more room if humans live forever. I mean, it's pretty outrageous. I mean, and it falls outside of our diet and lifestyle program for sure. But I think it's It's interesting. I think it's something that we should be considering. I mean, we do have these Yamanaka factors. We do have CRISPR now. We have, the longevity space, as we were talking about earlier, is, just massively exploding, and billions and billions and billions of dollars are just being poured into it. Altos Lab, which is rumored to be, funded by Jeff Bezos, has hired like the best and brightest longevity biogerontologists from around the world. And it's not just in California. I think it's in Cambridge in the UK. I think it's also in Asia. And the best, like Yamanaka himself has been recruited to Altos. I mean, the guy who discovered, who got the Nobel for Yamanaka factors is now at, the supposedly Bezos funded Altos Lab. Yeah.
Wow.
Yeah. Steve Horvath, who published the first clock, is at Altos.
Oh, really? I didn't
As
know
is
that.
Morgan Levine, his, extraordinary postdoc who was at Yale. She's now, I mean, I think there's a bunch of Nobels. So this is it.
Yeah. I mean, and it's fascinating, and it's amazing work. And at the same time, we can't lose sight of what makes life worthwhile in the first place.
Yeah, that's right. I think these conversations, Jeff, are just going to become all the more important.
Hey, I'm glad you enjoyed this video. We have conversations with today's top thought leaders every single week, so make sure you click the notification bell below so you don't miss our weekly videos. I'll see you soon.